Creating lighter and stronger parts with traditional methods is challenging. Often designers start new designs based on their experience of existing designs. They might take apart and start removing material in regions where it is redundant, using simulation to guide and verify the design. Radically new design concepts may not be considered due to time constraints, and the end solution may be over-designed for the particular application. Topology optimization in Siemens NX mimics nature's evolutionary approach to design, removing material based on the stress calculated at each node. To demonstrate the value of topology optimization, we're going to look at the design of the elevator bell crank in this plane. The elevator bell crank is a critical mechanical component that connects the actuation from the pilot's joystick directly to the elevators that control pitch. Here is the original design. Instead of using the designer's imagination for the redesign, they use the power of topology optimization to suggest a new design. The designer first starts with a model of the design space, the area that the new crank could fit within. In this case, the grey area is the design space. Only half of the space is modelled as it is a symmetric part. The red area represents the area where we don't want material to be placed for the design. The designer picks the topology optimization solution from the NX interface and follows the simple commands in the menu that are laid out in the steps of the process. First, the designer identifies the design space, symmetry plane, and material for the design space. The designer also notes that there are pin connectors within the design space. The optimization will maintain these when determining the part shape. The designer also identifies the red areas as keep-out zones. Next, the designer defines the loads that the part will experience at the pin connections. The final step before running the simulation is to set up the optimization targets. The target mass is set to 0.17 kilograms. The topology optimization run is then submitted. It takes some time to run through all of the iterations. Once the optimization is complete, the results of the new shape are created in the form of facet data. The new part is shown here in blue. If you isolate the part and its design space, you can get a better feel for the new part shape and how it is radically different from the original one. Traditional CAD tools can't do precise design operations on the facet models like this one. You would need to completely remodel the design using the facet model as a guide to get usable geometry that you can refine. However, in NX, even though this part is in the form of facet data, you can continue to refine the shape using convergent modelling. In this example, the designer feels they want to increase the material around the short connecting strands at each side of the part. The designer can use the Realise Shape commands within NX to reshape the geometry. The designer defines a tube cage in the region to be modified. The designer can then transform the shape by pushing and pulling the vertices of the cage. The designer can then apply a symmetric plane, and any further modifications are applied to both sides. Once complete, the designer unites the geometry to create the final shape. This final part is lighter and stronger than the original, and by letting the software iterate the solution, NX Topology Optimization opens up a range of new opportunities within design and engineering. Components can be designed faster and can take on unique shapes. System design can be reconsidered and multiple parts can be combined into one. For more information on NX functionality, please visit our NX playlist on our YouTube channel. Thank you for watching.